I am Priti Patidar at Index Institute of Pharmacy, Malvanchal University, Indore. Today's topic is alkenes, and conjugated peptides. Now, alkenes. Alkenes are the simplest class of organic compounds. They are made of carbon and hydrogen atom only and contain two types of bonds, carbon to carbon single covalent bond and carbon to hydrogen single covalent bond. They do not have functional groups. Alkenes form a homologous series with the general formula CnH2n plus 2, where n is the number of carbon atoms in the molecule. The first member of the family has the molecular formula CH4, where n equal to 1, and it is commonly known as methane, and the second member with molecular formula C2H6, where n equal to 2, is called ethane. These compounds are also known as the saturated hydrocarbons. These hydrocarbons are relatively unrelative under ordinary laboratory conditions, but they can be forced to undergo reaction by restricted treatment. It is for this reason that they were named prephene. For example, methane and ethane. Now, sp3 hybridization of alkanes. According modern orbital theory, carbon has electronic configuration. See ground state 1s2, 2s2, 2px1, 2py1, 2pz0. See excited state 1s2, 2s1, 2px1, 2py1, 2pz1. 1 2s and 3 2p orbital gives 4 new sp3 orbitals. The four new sp3 orbitals are arranged in space in such a way that their axes are directed towards the corners of regular tetrahedrons. In the formation of a methane molecule, the sp3 orbitals overlap with one s orbital of 4 hydrogen atom to form 4 ssp3 sigma bonds. In ethane molecule, sp3 orbital of one molecule overlap with sp3 orbital of the other carbon. The remaining three sp3 orbital of each of the two carbons overlap with the is one s orbital of H atom to form ssp3 sigma bond. This is the orbital structure of methane and ethane. Now, alkenes. Alkenes are hydrocarbon that contains a carbon to carbon double bond in their molecule. Molecular formula of alkenes are CnH2n, where n number of carbon atoms. Alkenes are commonly known as olefins. For example, ethene, CH2 double bond CH2, and 1-butane, CH2 double bond CH single bond CH2 single bond CH3, and 2-butene, CH3 single bond CH double bond CH double bond CH3. Now, sp2 hybridization. In ethylene, the carbon atom are sp2 hybridized. They are attached to each other by a sigma bond and pi bond. The sigma bond results from overlap of one sp2 hybrid orbital from one with sp2 hybrid orbital of another carbon. The pi bond is formed from overlap of unhybridized p orbitals. Remaining sp2 orbitals form sigma bond with hydrogen atom. Now, method of preparation of alkenes. First, hydrogenation of alkenes and alkynes. Second, reduction of alkyl halides. Third, decarboxylation of carboxylic acids. Fourth, Hydrolysis of Grignard reagent. Fifth, action of sodium on alkyl halides. Watts reaction. Sixth, Corey-House alkane synthesis. Seventh, electrolysis of salt of carboxylic acids or Kolb's method. Now, hydrogenation of alkenes and alkynes. Alkenes can be prepared by the catalytic hydrogenation of unsaturated hydrocarbon in the presence of catalyst nickel or platinum at 200 degree to 300 degree Celsius. For example, alkenes C R bond to R single bond CH double bond CH2 plus H2 in the presence of nickel gives us R single bond CH2 single bond CH3 alkanes. Second, propene CH3 single bond CH double bond CH2 plus H2 in the presence of nickel gives us CH3 single bond CH2 single bond CH3 propane. Alkene R single bond C triple bond CH plus 2H2 in the presence of nickel gives us R single bond CH2 single bond CH3 alkane. Methyl acetylene CH3 single bond C triple bond CH plus 2H2 in the presence of nickel gives us CH3 single bond CH2 single bond CH3 propane. Now, reduction of alkyl halides. Alkyl halides undergo reduction with nascent hydrogen in presence of reducing agent like zinc and HCl to form alkanes. For example, alkyl halides Rx plus H2 in the presence of nickel and HCl gives us alkane RH plus HX. Methyl iodide CH3 bond I plus H2 in the presence of zinc and nickel gives us CH3 single bond H methane plus HI. Now, decarboxylation of carboxylic acid. When sodium salt of carboxylic acid is heated strongly with sodaline NaOH plus CaO to form sodium carbonate and alkane. Sodium salt of carboxylic acid R bond COO Na plus NaOH. It gives us alkane R bond H plus Na2CO3. CH3 bond single bond COO sodium acetate plus NaOH gives us CH3 bond H methane plus Na2CO3. Now, hydrolysis of Grignard reagents. Alkyl magnesium halides Grignard reagent are obtained by treating alkyl halide with magnesium in anhydrous ether to give alkanes. Alkyl halides Rx plus magnesium Mg in the presence of ether gives us alkyl magnesium halides RMGX. RMGX plus H bond OH gives us R bond H alkane plus MgXOH. CH3 MgL methyl magnesium iodide MgI plus H bond OH gives us CH3 bond H methane plus MgIOH. Now, what synthesis? High alkanes are produced by heating an alkyl halide with sodium metal in dry ether. Two molecules of alkyl halides lose their halogen atom as NX. This net result is the joining of two alkyl groups to yield symmetrical alkane having even number of carbon atoms. Alkyl halide Rx Na2Na Rx in the presence of ether gives us RR symmetrical alkane and 2NaX. CH3 bond Br methyl halides 2Na CH3 bond single bond Br in the presence of ether gives us CH3 bond CH3 ethane and N2NABr. Now, Corehouse alkane synthesis. An alkyl halide is first converted to lithium dialkyl copper and then treated with an alkyl halide to give an alkane. CH3 single bond CH2 single bond Cl plus 2 Li in the presence of ether. CH3 single bond CH2 single bond Li plus LiCl. CH3 single bond CH2 single bond Li Cul in the it gives us LiCH3 single bond CH2 2 Cu plus Li I. LiCH3 single bond CH2 whole 2 Cu CH3 single bond CH2 single bond Cl gives us CH3 single bond CH2 single bond CH2 single bond CH3 plus LiCl plus CH3 single bond CH2 single bond Cu. Now called electrolysis method. Alkanes are formed on electrolysis of concentrated aqueous solution of sodium or potassium salt or saturated monocarboxylic acid. R bond COO Na plus H2O on electrolysis gives us R bond R plus 2CO2 plus 2NaOH plus H2. Now reactions of alkanes. First, substitution reaction as halogenation, nitration and sulfonation. And second, thermal and catalytic reaction has oxidation, pyrolysis cracking, isomerization and aromatization. First, halogenation. It involves the substitution of H atom of alkanes by as many halogen atoms by chlorine, chlorination, by bromine, bromination, by iodine, iodination, or by fluorine, fluorination. Methane reacts with chlorine in the presence of ultraviolet light or at high temperature 300 degrees Celsius to yield methyl chloride or chloromethane and hydrogen chloride. Methane CH4 plus chlorine Cl2 in the presence of UV light gives us CH3Cl plus HCl methyl chloride. The chain initiation step. Cl bond Cl gives us Cl plus Cl. Chain propagation step. Cl H bond CH3 gives us C bond Cl plus CH3. Chain termination step. CH3 plus Cl gives us CH3 bond Cl. Nitration. When alkane react with nitric acid at high temperature 400 degree to 500 degrees Celsius to form nitroalkane, RH plus OH bond NO2 at the 400 to 500 degrees Celsius temperature gives us R bond NO2 plus H2 and CH3 bond H methane plus OH bond NO2 at degree 400 to 500 degrees Celsius gives us CH3 single bond NO2 plus H2O nitromethane. Chain initiation step. HO bond NO2 gives us OH plus NO2. Chain propagation step. H bond CH3 at 400 to 500 degrees Celsius temperature gives us H plus CH3. Chain termination step. CH3 plus NO2 gives us CH3 bond NO2. OH plus H gives us H2O. Now, sulfon- sulfonation. This involves the substitution of a hydrogen atom of alkane with SO3H. When performed reaction of alkane with fuming sulfuric acid to give alkane sulfonic acid. Alkane RH plus sulfun, sulfonic, uh, fuming sulfuric acid HO single bond SO3H gives us alkane sulfonic acid R bond SO3H plus H2O. Now, combustion or oxidation. Combustion of alkane gives carbon dioxide and water. The general equation for the combustion of a hydrogen is given below. CXHY plus X plus Y fourth O2 gives us XCO2 plus Y, Y half H2O plus heat. Pentane C5H12 plus 5 plus 12 fourth O2 gives us 5CO2 plus 12 half H2O plus heat. Now, pyrolysis or cracking. The decomposition of compound by heat is called pyrolysis. The process when applied to alkene is known as cracking. Larger alkenes are broken into a mixture lower molecular weight alkenes and hydrogen. Ethane CH3 bond CH3 in the absence of air at 500 degree Celsius temperature gives us ethene CH2 double bond CH2 plus methane 2CH4 plus 2H2. Now mechanism of pyrolysis or cracking. Chain initiation step. CH3 single bond CH3 gives us 2CH3. Chain propagation step. CH3 plus H bond CH2 bond CH3 gives us at 500 degrees Celsius CH3 bond CH2 plus CH4. Chain termination step. H single bond CH2 gives us H CH2 double bond CH2. Now, isomerization. Normal alkanes are converted to their branch chain isomers in the presence of aluminum chloride and HCl. For example, N-butane is converted into isobutane. Now, N-butane CH3 single bond CH2 single bond CH2 single bond CH3 and in the presence of A AlCl3 and HCl it gives us isobutane. Now, aromatic, aromatization. Alkanes containing 6 to 10 carbon atoms are converted into benzene and its homologous at high temperature and in the presence of a catalyst. For example, an hexane is passed over Cr2O3 supported over alumina at 600 degrees Celsius to form benzene. An hexane CH3, CH2, 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 CH3 in the presence of Cr2O3 or Al2O3 at the 600 degrees Celsius it gives us benzene plus 4H2. Now uses of graphene. Graphene is widely used as fuel for jet engines and rocket and as fuel or a fuel component of for diesel and tractor engines. Paraffin is the most widely used heating oil in home central heating system in the UK, and it is still used in less developed countries as the main fuel for cooking. Liquid paraffin can be used as a lubricant for machinery. It is commonly used to treat dry skin, constipation, and eczema. Paraffin wax is also used as water harvesting soil treatment to supply runoff water to dry areas, as an adhesive and as a waterproofing agent. Now, preparation of alkenes. First, dehydration of alcohol. Second, dehydrohalogenation of alkyl halides. Third, dehalogenation of vicinal dehalides. Fourth, controlled hydrogenation of alkynes. Fifth, cracking of alkanes. Now, dehydration of alcohol. When alcohol is heated in the presence of sulfuric acid to form alkene by elimination of water. For example, alcohol in the presence of H2SO4 gives us alkenes plus H2O. Here, 1 propanol in the presence of H2SO4 gives us propene plus water. Now, dehydrohalogenation of alkyl halides. When alkyl halide is heated with the alcoholic solution of sodium hydroxide to form alkene and halogen halides. For example, alkyl halide in the presence of NaOH in alcohol gives us alkene plus water plus halogen halide HX. Now, propyl chloride in the presence of NaOH and alcohol gives us propene plus elimination of water plus HCl, which is hydrogen halide. Now, dehydrohalogenation of alkyl halides accepts rule. If the dehydrogenation of alkyl halide can yield more than one alkene according to Zetsef rule, main product is the most highly substituted alkene. For example, when 2-bromobutane is heated with alcoholic KOH to form 80% 2-butene and 20% 1-butene. Now, 2-bromobutane in the presence of KOH and H2O gives us carbocation 2 carbocation. Now, dehydrogenation of alkyl halides beta elimination reaction. Even mechanism. In this mechanism, breaking of the CX bond is complete before any reaction occurs when base 2 lose hydrogen and before the carbon to carbon double bond is formed. This mechanism is designed even E elimination 1 unimolecular. For example, reaction of 2-bromo 2-methyl propane to form 2-methyl propene, which follows two-step mechanism via carbocation intermediate. For example, 2-bromo 2-methyl propane plus methanol CH3OH gives us 2-methyl propene. Now, even mechanism. This step 1 2-bromo 2-methyl propane, its slow rate determining gives us carbocation plus Br, where step 2 is fast. Now, dehydrogenation of alkyl halides beta elimination reaction. E2 mechanism. This concerted process. E stand for elimination, 2 stand for bimolecular because the base remove a beta hydrogen at the same time its CX bond is broken to form alkyl halide. The rate law for the rate determining step is depend on both the alkyl halide and base. Rate K alkyl halide and base. If base is strong then E2 mechanism is operated. For example, N-bromopropane plus CH3 single bond CH2OH in the presence of NaOH gives us propene plus NaBr plus ethanol plus water. E2 mechanism. In this mechanism, proton transfer to the base, formation of carbon to carbon double bond, in ejection of bromide ion occurred simultaneously. That is, all bond forming and breaking occurred at the same time. Product is formed according to Satter's rule. Now E1 versus E2 or difference between E1 and E2. E1 is the unimolecular reaction and E2 is the bimolecular reaction. E1 two-step reaction and E2 is one-step reaction. The carbocation intermediate is formed in E1 and E2 no carbocation intermediate is formed. In E1 no transition state is formed and E2 transition state is formed. E1 molar protic solvent is good and in E2 molar aprotic solvent is best. In E1 strong nucleophile not interferes reaction and in E2 strong nucleophile faster than the reaction. E1 slow rate determining step and E2 fast rate determining step. In E1 rearrangement may take place and in E2 there is no rearrangement. In E1 bond formation and bond breaking is not simultaneous and E2 bond formation and bond breaking is simultaneous. In E1 reaction rate is increased when substrate concentration reaction and E2 reaction rate is increased when substrate and base concentration increases. In E1 no stereotype is specific and E2 anti-peripennular stereospecific. In E1 follows Steffes rule and E2 follow Satisfac rule. In E1 beta elimination and E2 also beta elimination. Now factor affecting on E1 and E2. E1 good living group alcohol and in E2 better living group faster than the reaction. In E1 reactivity order is 3 degree greater than 2 degree and 2 degrees greater than 1 degree. In E2 reactivity order is 3 degrees greater than 2 degree, 2 degrees greater than 1 degree. And E1 stable carbocation tertiary carbocation and in E1 weak base water or alcohol and in E2 favored by strong bases. In E1 polar protic solvent and in E2 polar aprotic solvent. In E1 only substrate concentration faster the reaction and E2 substrate concentration as well as strong base faster the reaction and E1 first order kinetics and E2 second order kinetics. Now dehalogenation of vicinal dihalides. Dehalogenation involves the removal of a molecule excess from a recent reactant molecule. A compound having two halogen atoms on adjacent carbon atom called a vicinal dihalide or weak dihalide. The treatment of Weak D halides with zinc dust using ethyl alcohol as solvent result in dehalogenation and an alkene is formed. Weak D halide plus zinc in the presence of ethanol gives us alkene plus ZnBr2. 1,2-dibromopropane plus Zn in the presence of ethanol gives us propene plus ZnBr2. Now, control hydrogenation of alkyne. Alkynes undergoes hydrogenation in the nickel or palladium or platinum to form alkenes. Alkyl R single bond C triple bond CH plus H2 in the presence of nickel at 250 to 300 degrees Celsius, it gives us R single bond CH double bond CH2 and methyl acetylene CH3 single bond triple bond CH plus H2 in the presence of nickel at 250 to 300 degrees Celsius gives us CH3 single bond CH double bond CH2 ethene. Now, pyrolysis or cracking. The decomposition of a compound by heat is called pyrolysis. This process, when applied to alkane, is known as cracking. Larger alkanes are broken into a mixture lower molecular weight alkane, alkenes, and hydrogen. Ethane CH3 single bond CH3 at the 500 degrees Celsius and absence of air, which gives us ethene CH2 double bond CH2 plus methane 2CH4 plus 2H2. Now, reaction of alkenes, addition of hydrogen halide, addition hypohalose acids, addition of sulfuric acid, addition of water, addition of halogens, addition of hydrogen, catalytic oxidation, oxidation with potassium permanganate, ozonolysis, polymerization, oxymercuration, demercuration of alkenes. Now, electrophilic addition reaction. Alkene contain carbon to carbon double bond to which treatment of halogen halides. Initially addition of halogen electrophile to form carbocation. Carbocation attack by halide nucleophile to form a addition product. That addition reaction is called as electrophilic addition reaction. For example, ethylene CH2 double bond CH2 plus HBr gives us ethyl bromide CH3 single bond CH2 single bond Br. Now, addition of hydrogen halide. Alkenes react with hydrogen halides HCl, HBr or HI to form alkyl halides. Ethylene CH2 double bond CH2 plus HBr gives us ethyl bromide CH3 single bond CH2 single bond Br. And 2-butane plus HBr is gives us 2-bromobutane. Now, Markovnik rule. If alkene is unsymmetrical, the H plus or HX goes to the double bonded carbon that has already greatest number of hydrogen. For example, reaction of HCl with propene yield 2-chloropropane. Propane CH3 single bond CH double bond CH2 at the presence of HCl gives us 2-chloropropane. Formation of carbocation. Two types of carbocation are possible. Bromide ion attacks the more stable secondary carbocation. The order of stability of carbocation is 3 degrees greater than 2 degree, 2 degrees greater than 1 degree. Secondary carbon has lower energy. More stable secondary carbocation has lower energy transition state and faster rate of formation. Antimarconic rule. The H plus of HX goes to the double bonded carbon that has already listed under number of hydrogens in presence of peroxide is known as antimarconic rule. For example, propylene react with HBr in the presence of by a free radical mechanism. Now some difference between Marconic rule and anti-Marconic rule. H- in Marconic rule, H of goes to double bonded carbon atom which has greatest number of hydrogen atom, and in anti-Marconic rule, H hydrogen of goes double bonded carbon atom which has least number of hydrogen. In Marconic rule, initially hydrogen goes to carbon to carbocation. In anti-Marconic rule, initially halogen goes to carbon atom which has greatest number of hydrogen atom. In Marconic rule, secondary carbocation intermediate formed. In anti-Marconic rule, secondary free radical intermediate formed. In Marconic rule, peroxide effect is not considered. In anti-Marconic rule, peroxide effect is considered. In a Marconic rule, electrophilic addition reaction is occurred. In anti-Marconic rule, free radical addition reaction is occurred. Now, mechanism of anti-Marconic rule free radical addition reaction. Peroxide dissociate to give alkoxy free radicals. Alkoxy free radicals attack HBr to form a bromine atom free radical. Bromine atom can attack propylene to give a primary free radical and secondary free radical. More stable secondary free radical attacks H plus from form N propylyl bromide. R bond O bond R gives us 2R bond O. Now addition of hypohalous acids. Alkenes react with hypohalous acid to give halohydrines. For example, CH2 double bond CH2 plus HOCl gives us ethylene chlorohydrin. Now, addition of sulfuric acid. Sulfuric acid undergoes addition reaction to an alkene to form alkyl hydrogen sulfate. For example, propyl 1-ene gives us isopropyl hydrogen sulfate. Now, addition of water. Water adds to alkene in presence of acid catalyst form alcohol. For example, propene CH2 single bond CH double bond CH2 plus H2O in the presence of H plus ion gives us 2-propanol. Now, halogenation of alkenes. When alkene is treated with halogen in presence of sodium chloride to give dihalogenated alkane. For example, when ethene is reacted with chlorine in presence of sodium chloride to form 1,2-dichloroethane. Ethene CH2 double bond CH2 plus Cl2 in the presence of NaCl gives us 1,2-dichloroethene. Now, addition of hydrogen. Alkanes can be prepared by the catalytic hydrogenation of unsaturated hydrocarbon in the presence of catalyst nickel or platinum at 200 degree to 300 degrees Celsius. Alkene R1CH double bond CH2 plus H2 in the presence of nickel gives us alkane. R bond CH2 single bond CH3. Now, catalytic oxidation. Alkenes add on oxygen atom across the carbon to carbon double bond when react with oxygen O2 in the presence of silver catalyst to form epoxides. For example, ethylene undergoes oxidation in presence of silver catalyst to form ethylene oxides. For example, ethylene CH2 double one CH2 plus half O2 at the presence of silver catalyst it gives us oxyren. It means ethylene oxides. Now, oxidation with KMNO4. Treating of alkenes with cold dilute basic KMNO4 leads to 1,2 diols means vicinal diols. For example, ethylene react with cold dilute basic K-amino4 to form ethane 1,2 diols. Ethylene CH2 double one CH2 plus KMNO4 in the presence of NOH gives us ethane 1,2 diol. Now, ozonolysis. When ozone is passed through a solution of an alkene in an inward solvent CHCl3 or CCl4 at low temperature is reacted by addition across the carbon-carbon double bond of alkene. First, an unstable intermediate molozonide is formed which spontaneously isomerizes to give the ozonide. Ozonide decomposes in presence of zinc to form carbonyl compound. Now, polymerization. Two or more alkenes join together to form new compound which has several identical units. That reaction is called as polymerization. Addition of alkene together without any loss of atom. That polymerization is called addition polymerization. For example, ethylene CH2 double one CH2 at the 200 degrees Celsius it gives us CH2 single one CH2 single one CH2 single one CH2 means polyethylene. Now, oxymercuration, demercuration of alkenes. Mercuric acetate and water add to alkenes called as oxymercuration. Reduction of oxymercuration product in presence of sodium borohydride to form alcohol called as demercuration. For example, prop 1 in the presence of H2O, it gives us 2-propanol. Now, oxymercuration demercuration of alkene mechanism. Prop 1 in is now dienes. An unsaturated hydrocarbon containing two double bonds between carbon atoms are called as dienes. Isolated dienes double bond are separated by more than one single bond. Conjugative dienes double bond are separated by one single bond. Cumulated dienes double bond are adjacent. The cumulative dienes CH3 single bond CH double bond C double bond CH single bond CH3 and conjugated dienes CH3 single bond CH, double bond CH, single bond CH, double bond CH, single bond CH3. And isolated dienes CH2, double bond CH, single bond CH2, single bond CH, double bond CH2. Now preparation of conjugative dienes. First, 1 butene in the presence of HBr and Br2. It form 1,3 butadienes. Now, Diels-Alder reaction. It includes the reaction between 1,3-butadienes and ethene to form cyclohexene adduct. 1,3-butadiene plus ethene gives us cyclohexene. Now, electrophilic addition of conjugative dienes. Dienes are treated with hydrogen halide to undergoes 1,2 and 1,4 addition. Now, addition of hydrogen halides. Dienes are treated with halogen halide to undergoes 1,2 and 1,4 addition. Now, addition of halogens. Dienes are treated with halogen to undergoes 1,2 and 1,4 addition. Now, addition of water. 1,3-butadiene react with water in the presence of H2SO4 to give a mixture of 1,2 and 1,4 addition. Now, addition of hydrogen. Dienes are treated with hydrogen to undergoes 1,2 and 1,4 addition. Now, polymerization. 1,3-butadiene polymerizes in the presence of peroxide to give polybutadiene. Now, free radical addition of conjugated dienes. Dienes also undergoes free radical chain reaction to form 1,4 addition product. Now, alicyclic rearrangement. The alicyclic compounds are those which have a functional group on a carbon atom alpha to a is directly proportional to an alphinic bond. Allylic compounds undergoes acid or base catalyzed migration to form new compounds. Now, stability of alkenes. Tetra-substituted alkenes are more stable than tri-di-mono-substituted alkenes. In di-substituted alkenes, trans form is more stable than cis form of di-substituted alkenes because more substitution leads to more conjugation directly proportional to stability. Hyperconjugation means a number of alpha hydrogen to alpha carbon atoms. Less stable isomers has higher energy which is identified by heat of hydrogenation. For example, cis-2-butene exert 28.6 kcal by mole energy while trans-2-butene exerts 27.6 kcal by mole energy on hydrogenation of 2-butene. Now, stability of conjugated dienes. Conjugated dienes are more stable than isolated dienes because conjugative dienes show resonance stabilization effect by isolated dienes does not show resonance stabilization. Stability of alkenes. So resonance stabilization. Thank you.